Welcome to today's session. We'll be exploring an interesting problem titled Find All Duplicates in an Array. In this problem, we aim to identify all elements in an array that appear more than once. It's a great problem to enhance your understanding of array manipulation and optimization techniques. Let's dive in. In this problem, we are given an integer array called nums, which has a length of n. Every integer in this array is guaranteed to fall within the range from 1 to n. Additionally, each number in the array will appear either once or twice. Our task is to find all the numbers that appear twice and return them as a list. The key challenge of this problem is to design an algorithm that works efficiently in n time complexity while using only constant extra space. Let's look at the input format. We are provided with an array nums where each value satisfies the condition 1 equals nums, I equals n. The output format is a list of integers, containing all the values that appear twice in the array. Now let's consider an example. If the input array is 432782231, the numbers 2 and 3 both appear twice. Therefore, the correct output is 2, 3. Here's a closer look at the first example. In the array 432782231, the numbers 2 and 3 each occur twice, which is why they are included in the output. It's important to note that the order of the output does not matter. 3 and 2 would also be a valid answer. Now, consider another example. If the input is 112, the only number that appears twice is 1. Thus, the output is 1. Finally, if the input array is 1, there are no duplicates in the array. As a result, the output would simply be an empty list. In the example where nums is 1, the output is an empty list because no number appears more than once. This brings us to the problem's constraints. The length of the array, n, can range from 1 to 10⁻⁵. Each integer in the array is guaranteed to be within the range from 1 to n, and each number will appear either once or twice. These constraints highlight the need for an efficient solution. Let's also address some edge cases. For the minimum input, such as nums equals 1, where there are no duplicates, the output is. For a case with a single duplicate, such as nums equals 1, 1, the output is 1. Similarly, if all values in the array are unique, like in nums equals 1, 2, 3, 4, the output is again an empty list. Now, consider a scenario where every number in the array appears twice. For example, if nums equals 1, 1, 2, 2, 3, 3, all three numbers 1, 2, and 3 are duplicated, so the output is 1, 2, 3. Finally, we must account for large input sizes. When n is as large as 10⁻⁵, the algorithm must efficiently process the data in n time and use only 1 extra space. This ensures that the solution can handle even the largest valid input sizes without running into performance or memory issues. With these constraints and edge cases in mind, we are ready to think about how to design an optimal solution for this problem. To solve the problem of finding all duplicates in an array, we start with the brute force approach. The intuition here is straightforward. We compare every pair of elements in the array to identify if any number appears more than once. This is done by iterating through the array with nested loops and counting occurrences explicitly. If a number is found twice, it is added to our result list. While this method is easy to implement and doesn't require additional memory, it is computationally expensive. With a time complexity of n squared, due to the nested loops, this approach becomes impractical for larger input sizes. Although it uses constant space, the inefficiency of its runtime makes it unsuitable for scenarios where performance is critical, such as competitive programming. A more efficient solution can be achieved using the hashing approach. The key idea here is to utilize a hash set to keep track of numbers as we iterate through the array. Whenever we encounter a number, we check if it already exists in the set. If it does, we recognize it as a duplicate and add it to the result list, otherwise, we insert it into the set. This method significantly improves the time complexity to n, as we only traverse the array once and each set operation, checking or inserting, is constant time. However, the trade-off is the additional space requirement of n for the hash set, which might be a limitation in memory-constrained environments. While more efficient than brute force, this approach may not be ideal if space optimization is a priority. An even more optimized solution leverages the cyclic sort-based approach. This method takes advantage of the fact that the array contains numbers within the range 1 and n. By using the array itself as a structure to track duplicates, we can achieve both time and space efficiency. The process involves iterating through the array and, for each number, calculating its corresponding index as abs, nums, I1. If the value at this index is already negative, it means the number has been seen before, so we add it to the result list. If not, we mark the number as visited by negating the value at that index. This approach runs in O(n) time since each element is processed once, and it requires O(1) space as no additional data structures are needed. However, it modifies the input array, which may not always be acceptable, though this can be addressed by restoring the array if necessary. Overall, this method strikes an excellent balance between performance and resource usage. The cyclic sort-based approach emerges as the most suitable solution for this problem. Its optimal time complexity of O(n) ensures that the solution can handle large datasets efficiently, while its O(1) space usage makes it ideal for memory-constrained environments. A key insight that drives this approach is recognizing that the array's values, constrained to the range 1en, can be used as indices to track duplicates directly. This eliminates the need for extra space like a hash set. While it does involve modifying the input array, the trade-offs are well justified given the superior balance of time and space efficiency. In conclusion, this approach is the most practical and elegant solution, especially when compared to the hashing method, which requires additional memory. Its ability to optimize both performance and resource usage makes it the clear choice for solving this problem effectively. To start, the problem asks us to determine if there are any duplicate elements in a given array of integers. One straightforward way to solve this is by using a brute force approach. The idea here is simple: for every element in the array, we compare it with all other elements to see if there's a match. To implement this, we use two nested loops. The outer loop starts at the first index and progresses through the array, while the inner loop starts right after the current position of the outer loop and compares the two values. If we find any pair of elements that are equal, we return true, indicating a duplicate exists. If, after all possible comparisons, no duplicates are found, we return false. However, this approach has a major drawback: its time complexity is O(n squared), because we are comparing all possible pairs in the array. While it doesn't require extra space, this inefficiency makes it impractical for larger datasets. A more efficient approach involves using a hash set. Instead of comparing every pair of elements, we can use the hash set to keep track of numbers we've already encountered. As we iterate through the array, for each number, we check if it's already in the hash set. If it is, that means we've seen it before, and we can immediately return true. Otherwise, we add the number to the hash set and continue. By the end of the iteration, if no duplicates are found, we return false. This approach significantly improves the time complexity to O(n), as we only traverse the array once, and operations like checking for existence and inserting into a hash set are O(1) on average. However, it does use additional space proportional to the size of the array, as we need to store elements in the hash set. When comparing the two approaches, the brute force method is much simpler to understand but inefficient for larger arrays due to its O(n squared) time complexity. In contrast, the hash set approach drastically reduces the time complexity to O(n) by avoiding redundant comparisons. The use of a hash set also ensures highly efficient lookup and insertion operations, making it well suited for this problem. Furthermore, it's important to consider edge cases. For instance, if the input array is empty or contains only one element, we can immediately return false, as there are no duplicates to find. If all elements in the array are distinct, the hash set ensures no false positives. Additionally, in cases where the array contains only duplicates, the algorithm efficiently identifies the first duplicate during traversal without unnecessary checks. In terms of data structures, the hash set is pivotal here due to its fast lookup and insertion times. It ensures we only store unique elements as we traverse the array, making it both time efficient and appropriate for the problem. The input array itself remains unchanged throughout the process, as the algorithm operates directly on it. To illustrate, consider the example array 1, 2, 3, 4, 2. We initialize an empty hash set. As we iterate, we first encounter the number 1, which isn't in the set, so we add it. Next is 2, which also isn't in the set, so we add it as well. Then we process 3 and 4 in the same way, adding them to the set. When we reach the second occurrence of 2, we find it already exists in the set, signaling a duplicate. At this point, the algorithm returns true, demonstrating its early exit feature and efficiency. The result of the example is true, as we identified a duplicate in the array. This highlights a key optimization of the algorithm. It stops as soon as a duplicate is found, avoiding unnecessary computations. While the hash set does use additional memory, this spacetime trade-off is justified by the significant improvement in time complexity compared to the brute force approach. This method is particularly valuable in real-world scenarios where fast duplicate detection is essential, such as in data validation or when processing large datasets. By leveraging the strengths of hash sets, this algorithm achieves both speed and scalability without compromising accuracy. This implementation solves LeetCode problem number 442. Find all duplicates in an array using an efficient in-place algorithm. The goal is to find all numbers that appear twice in the array. The array contains integers in the range 1 to n, where n is the size of the array. Hashtag explanation. 1. Initialization. We start by creating an empty list result to store the duplicate numbers. 2. Main loop. We iterate through each element in the array using a for loop. The current index is I, and the value at nums, I, determines which index we need to check. Since the values are in the range 1 is n, we subtract 1 to find the corresponding index. Index equals abs, nums, I, 1. 3. Checking for duplicates. If the value at nums, index, is already negative, it means that we have seen this number before, so we append abs, nums, I, to the result list. Otherwise, we mark this number as seen by negating the value at nums, index. 4. Return result. After processing all elements, the result list contains all duplicate numbers, which we return as the output. Hashtag key features. In-place modification. The algorithm modifies the input array to track seen numbers by negating values. This avoids the need for extra space. Time complexity. The solution runs in O(n) time because each element is processed at most twice, once for marking and once for checking. Space complexity. It uses O(1) extra space, as no additional data structures are used. Hashtag edge case handling. If the input array is empty, the loop does not execute, and an empty list is returned. If there are no duplicates, the result list remains empty and is returned as such. This approach is efficient and adheres to the constraints of the problem, making it a robust solution to identify duplicates in an array. This is the Java implementation for LeetCode problem number 442, find all duplicates in an array. The logic mirrors the Python approach, using in-place modifications of the input array to track duplicates. Key differences include the use of Java's ArrayList for the result, explicit type declarations, and Java-specific syntax. The algorithm runs in O(n) time and O(1) extra space, making it efficient for larger inputs. To solve the problem, we use the input array itself to track the numbers we've seen. Starting with the input 432782231 and an empty result list, we iterate through the array. For each number, we calculate its index by taking the absolute value of the number and subtracting 1. In the first iteration, the number is 4, so the index is 3. Since nums, 3, is positive, we mark it as visited by negating it, resulting in the array 432-78231. Moving to the next number, 3, the index is 2. Again, nums, 2, is positive, so we negate it to mark it as visited, updating the array to 43-2-78231. This process continues. For -2, we calculate the index as 1 and negate nums, 1, making the array 4-3-2-78231. For -7, the index is 6, and we negate nums, 6, resulting in 4-3-2-782-31. Then, for 8, the index is 7, and we negate nums, 7, giving us 4-3-2-782-3-1. Now, we encounter 2 again, but this time nums, 1, is negative, indicating we've seen this number before. So, we add 2 to the result list. Similarly, for -3, we find nums, 2, is already negative and append 3 to the result. Finally, for -1, we mark it by negating nums 0, leaving us with the array -4 -3 -2 -7 8 2 -3 -1. The result list now contains 2 3. After completing the iterations for the first example, the final output is 2 3. Now, let's examine another example with the input 1 1 2. We start with the array as is and an empty result list. For the first number, 1, the index is 0. Since nums 0 is positive, we negate it, resulting in -1 1 2. For the second number, 1, the index remains 0. This time, nums 0 is already negative, so we append 1 to the result list. For the final number, 2, the index is 1. Since nums 1 is positive, we mark it as visited by negating it, leaving us with -1 -1 2. At the end of this process, the result list contains 1, which is the final output for this example. In the third example, the input array is 2 2 3 4 5 5, and we again start with an empty result list. The first number, 2, corresponds to index 1. Since nums 1 is positive, we negate it, resulting in 2 2 3 4 5 5. On encountering the second 2, the index remains 1, but nums 1 is now negative, indicating a duplicate. We append 2 to the result list. Next, we process 3, whose index is 2. Since nums 2 is positive, we negate it, giving 2 2 3 4 5 5. For 4, the index is 3, and we negate nums 3, updating the array to 2 2 3 4 5 5. Then, for 5, the index is 4. Since nums 4 is positive, we negate it, resulting in 2 2 3 4 5 5. Finally, encountering the second 5, the index remains 4, but nums 4 is already negative, so we append 5 to the result list. The iterations conclude with the result list containing 2 5, which is the final output for this example. In this solution, we focus on processing the input array in a single iteration while ensuring all operations are efficient. The outer loop iterates through each of the n elements in the array, and for each element, we perform a few constant time operations. These include calculating an index using the absolute value of the current number, checking if the corresponding value is already negative to determine if it's a duplicate, appending to the result list if necessary, and potentially negating the value to mark it as visited. Since these operations are repeated for each of the n elements, the total time complexity of the loop is O(n). Additionally, the index calculation and negation are simple arithmetic operations, each taking O(1). Appending to the result list is also O(1), and happens only once per duplicate. Altogether, this leads to an overall time complexity of O(n), proportional to the size of the input array. This solution is space efficient as it modifies the input array in place to track visited elements, eliminating the need for additional data structures. The input array itself is reused, so no extra memory is consumed aside from the input. The result list stores the duplicate numbers, and in the worst-case scenario, if every number in the array is duplicated, the result list could hold up to n/2 elements. However, this space usage is still directly proportional to the input size, making it O(n). Beyond these, the algorithm uses a few auxiliary variables, such as I4 iteration and index for calculations, which require only constant space. Therefore, the overall additional space complexity is O(1) as no significant memory is allocated beyond the input and output. When compared to a brute force approach, this optimized solution shines in efficiency. A naive method would involve nested loops where, for each element, the algorithm checks all subsequent elements for duplicates. This results in a time complexity of O(n², which is highly inefficient for large arrays. In contrast, the optimized solution reduces the time complexity to O(n) by leveraging the input array as a marker for tracking scene numbers. The space complexity in both approaches remains O(1), but the optimized solution achieves significant time savings. Considering best, average, and worst-case scenarios, the time complexity remains consistent at O(n). In the best case, with no duplicates, the algorithm still iterates through all elements. In the average case, with a typical distribution of duplicates, and the worst case, where every element is a duplicate, the algorithm performs O(n) operations. This consistency highlights its robustness and scalability. To mathematically prove the time complexity, we observe that the algorithm processes the array in a single pass using a for loop, resulting in exactly n iterations. Within each iteration, operations like index calculation, negation, condition checks, and appending to the result list are all constant time, or O1. Multiplying these constant operations by the total number of elements n gives a total time complexity of O(n). Furthermore, no additional data structures are used aside from the input array and the result list, which means the space complexity remains O1. This makes the solution both time-efficient and space-efficient, ideal for handling large datasets. One of the most common mistakes when solving this problem is not accounting for edge cases. For example, if the array is empty, contains just one element, or has duplicate elements clustered together, your solution might fail or produce runtime errors unless these scenarios are explicitly handled. Another mistake is relying on inefficient brute force methods, such as using nested loops. While this might work for small input sizes, it quickly becomes impractical for larger arrays, especially if the constraints allow sizes up to 10 to the power of 5. Additionally, modifying the input array directly, such as sorting it in place or altering its contents, can cause issues if the array is needed in its original form later. This is particularly important in scenarios where the input is treated as immutable. Finally, overlooking constraints like arrays with negative numbers can result in failure when using techniques such as index marking. Always ensure your solution is robust against the full range of inputs specified in the problem constraints. Another pitfall is assuming that the elements in the array are unique, which is not guaranteed in problems involving duplicates or frequency counts. Misinterpreting the problem statement in this way can lead to incorrect logic. On the bright side, recognizing common patterns can significantly streamline your approach to these problems. For instance, many array-related challenges can be reduced to familiar techniques such as sorting, using hash maps to count frequencies, or leveraging mathematical properties like the sum of integers. In interviews, it's also valuable to demonstrate the evolution of your solution from a brute force approach to an optimized one. This progression showcases your ability to analyze and improve efficiency. Similarly, discussing the trade-offs between time and space complexity, whether you prioritize in-place modifications over extra data structures, indicates a deeper understanding of algorithm design. Finally, proactively addressing edge cases during your explanation can leave a strong impression on interviewers, as it highlights your thoroughness and attention to detail. To broaden your understanding of related problems, consider exploring similar challenges on LeetCode. For example, Problem 217 contains duplicate, focuses on identifying whether any duplicates exist in the array. Problem 287, find the duplicate number, narrows the scope to locating a single duplicate in a specific context. Problem 448, find all numbers disappeared in an array, involves identifying missing elements instead of duplicates, while Problem 41, first missing positive, takes it a step further by finding the smallest missing positive integer. These problems offer opportunities to apply similar concepts while adapting to slightly different requirements, helping you strengthen your pattern recognition and problem-solving skills. There are several alternative approaches to solving this problem, each with its own advantages and trade-offs. A straightforward method is sorting the array, which takes n log n time. After sorting, you can scan through the array to identify duplicates or missing numbers. While this is simple and space-efficient, it's not optimal in terms of time complexity. Another popular approach is using a hash map to count the frequency of each element. This runs in n time and is easy to implement, but it requires additional space proportional to the size of the array. For problems where values are within the range, 1 each n, an in-place marking technique can be used. By marking indices, such as negating the value at a specific position, you can achieve n time an 1 space. However, modifying the input array can be problematic in certain contexts, and this method may not work if the array contains negative or out-of-range values. Lastly, mathematical formulas, like the sum of the first n natural numbers, can provide elegant n solutions without additional space. While highly efficient, these solutions may be prone to integer overflow in some programming languages, so care must be taken when implementing them. Great job! We've successfully tackled the problem and reviewed key concepts, including algorithm optimization and complexity analysis. Remember to keep practicing similar problems to sharpen your skills. Thank you for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!